How are you finding it?
It's a nice app.
Okay. Right, so today we are doing physics. I'm gonna start a new notebook, and I'll call it let's rename this. I don't know what to rename it. How do I rename it? That's how. It's what's the name of that chapter again?
Vertical projectile.
Vertical projectile in one dimension. Yeah, so 1D vertical projectile motion. All right. Just wanna have lines so that we can see. All right. Oh yeah. Okay. Okay, so now for today's science class, we're gonna start off with work example 2. All right.
What's the point of having lines if you're not going to write inside the lines?
Oh. They just help me to write straight. Not
It's
really.
not straight.
It's kind of more straight than it is from my angle.
Say, when you stress me, you stress me.
How am I stressful?
You're not writing inside the lines.
No, it's a mark of creativity, a heightened sense of creativity.
In the skew.
Yeah, man. Don't think too much about it. You won't be thinking about that when you're practicing for a test.
I will actually.
So we have this example where a cricketer is hitting a ball during a cricket match. And that ball gets hit all the way up. Gets hit so that it moves all the way up. Right?
Yeah.
We're told that if it takes 10 seconds to return to the initial height, so the whole trip up and down is 10 seconds. We must determine the maximum height that the ball reaches. That's what we must find. Yeah? So we need to find how high the ball goes. We know that the ball goes up and down, and that whole process takes 10 seconds. Yeah. Not a lot of information going around for us to work with, right?
Yes. I'm trying to think of the formulas.
Okay.
We still don't have initial velocity. At maximum height, our final velocity is going to be 0.
That's true. We don't know the initial velocity.
And then we have gravitational force.
But
which is
we
9.8 meters per
per second squared. Definitely. That's correct. So we've got the acceleration due to gravity, which is, we'll assume, since it's traveling down, it's 9.8 meters per second squared, right? But we know the velocity at the top,
Mm.
which is where it reaches the H max, which is at H max. We don't know its initial velocity, and yeah. So what can we do? I guess we are being creative, so we have to be creative. So it's useful to divide the motion in two parts. We have the motion up and the motion down. Okay. So if we do that into motion up and motion down. All right. So let's look at the problem a little bit different. We'll just draw something that looks like that. So initially our ball gets hit, right? Okay. Where was I? 1D vertical projectile motion. All right. So initially our ball gets hit, and that's where we have t equals 0 seconds, right? Somewhere at t equals tm, so the m is for max. The ball reaches its maximum height. Okay, just do that. And then at a certain point, it comes back down to Earth and it's traveling down. All this time, G acts on it vertically downwards, right? Alright, what our theory tells us is that the time to travel upwards is the same as the time to travel downwards. So if to travel from t equals 0 seconds to where it gets to its maximum height, then the time to travel down should be the same from there to there. So that means if we segment the time like that, if this is tm, this is also tm, then this means the time there is 2 times tm, right? And this is what equals 10 seconds. Okay, so at least we know that.
So TM could be 5 seconds.
We don't know, could be. But let's not go there for now. But we also know that up there, the velocity is 0 meters per second. Right. And this is where the time equals Tm. Alright. So yeah, we've divided our motion into two parts. The first part of the motion is the upward motion. The second part is the downward motion. At velocity VF, we have our H max, and we also know the velocity initial, or we don't know the initial velocity. Right, so if we choose, in our case, we chose down as negative, as negative.
So up is positive.
Up is positive, yeah. So we could work out the height it travels, which is h max, which is what we're supposed to find. If we use one of those equations, maybe we start with that one. We don't know what the initial velocity is, but we do know the velocity of the ball when it starts its descent. So when it starts its descent, it's 0.
Yeah, so we can use that as initial velocity.
As initial velocity for the downward movement. We know that gravity, or acceleration due to gravity rather,
Is negative.
acts on it, and it's negative. And I guess since the time to travel up is the same as the time to travel down, then from where v is 0 meters per second to when it comes back to the ground, that's 5 seconds. So if 2tn equals 10 seconds, then tm is 5 seconds. So we've got time. This we've got the acceleration due to gravity. This we've got, and it's that value. And we can find out how high the ball travels. And how we do that, we'll take the upward movement is initial velocity times time plus a half into acceleration due to gravity times t squared, which is 0, plus negative 9.8 times t squared. Oh, t squared is 5 squared, 100%. So let's just say 25. Then that becomes change in vertical height, in vertical displacement is 0 plus, or rather minus,
Negative 122.5.
122.5 meters, but we chose downward as negative. Therefore, the H max is 122.5 meters. Wow, he actually hit the ball quite high up, eh?
Yeah.
It's quite high up.
No, considering how cricket is, I believe it.
You believe it?
I believe it.
Do you think he hit a 6 or a 4?
It could be a 6.
Could
Because
be a
6
six.
goes really far.
Really far, yeah. Alright. Attributions, Sunil Kumar Singh. Okay. Let's do another word example.
Eiffel Tower.
A sequence of balls are successively dropped from the top of a tower. The time interval between the release of the balls is equal. At the precise instant that the 9th ball, or ball 9, is released, the first ball hits the ground. Oof. Which of the balls in the sequence is at 3/4 of the height h of the tower when the ball hits the ground, when the first ball hits the ground. Ooh. Okay. So we don't know how many balls in total are being dropped, but we know it's many. It's more
Let's
than
say
2.
5 balls.
Hmm?
5 balls.
5, it's more than 9. Because when the 9th ball is released, the first ball hits the ground.
The first ball is faster.
Well, I mean, they're all dropping at the same velocity, at the same rate of change of velocity. So, alright.
So do you think this person is dropping them one by one?
It's possible. So he's just standing there at the top of a tower. He's got a big basket of balls and he's counting 1, 2, 3, 4,
6, 7, 8, 9.
6, 7. So when the 9th ball gets released, the first ball hits the ground.
How big is the tower?
How tall is the tower?
Yeah, how tall is the tower?
I have no idea, but we're gonna find out, isn't it?
Eiffel Tower.
Because we're only told that which of the balls, so in other words between ball 1 and ball 9, which of them is at 75% of the height from which they drop it.
Oh, 7.
Let's try and work it out. Let's try and
Ball
work it
7
out.
or 6.
Think so?
Yeah.
Okay.
Because it can be 8.
So in any case, when the first ball is dropped, we'll say that's T0. Okay. Okay. After time Ti, the second ball is dropped. So we're gonna assume that they dropped at equal intervals of time. Right. After another interval, third ball is dropped. That means when ball 3 is dropped, the total time that has passed is 2t. So that means when 8 balls have been dropped, the total time should be 8t. Okay. First ball drops. Third ball drops, okay. So that means 3ti, fourth ball is dropped. 4ti, fifth ball is dropped. 5ti, sixth ball is dropped. 6ti, seventh ball is dropped. Oh man, why is my stationery not working? Oh, the battery. Ugh. Okay. I forgot to do that. Okay, it's gonna need like a minute. Should have charged it during break. I should have charged it during break. Wow, the pen really runs out of ink quick. Okay, so while I wait. Okay. So I'm done chewing. So now we know that the sequence is like that. Ball 1 drops. After time ti, second ball drops. And if the time intervals are the same, that means the fourth ball is dropped after 3, third time interval, fifth ball after the fourth time interval, and so on. Which means that so at no, I thought I could drop it, but clearly not. So it's not showing me so much battery. Okay. Anyway, so we know that the time intervals are like that. Now, if we are to describe the motion, or rather the events mathematically, we would have to use some creativity. And in order for us to do that, we will have to okay. The first ball, we'd have to consider that the first ball hits the ground when the 9th ball is dropped. So when the 9th ball is dropped, that's at 8 ti, right? After a total time of 9 minus 1 ti, which is 8 ti, that's when the 9th ball is dropped. Alright. The displacement of the first ball is described by the equation delta x, or delta y rather, since we've decided to go with that convention, and that equals initial velocity times time plus a half gravity acceleration times the time squared. The ball, each one of the balls when it's dropped, its initial velocity is 0. So for each drop ball, the initial velocity is 0. So that means this component falls off. Then we're left with a half times acceleration due to gravity times the time squared. And the balls are dropped, or rather, we know that for the first ball, it needs to have dropped a height of a half times acceleration due to gravity times 8 ti squared. This is for the first ball. The reason it's for the first ball is because it would have traveled that much time. So this is the amount of time it would have taken for it to hit the ground, which will give us h max from the top of the tower, or wherever the height of the tower is. Now, if the nth ball is at 3/4 of the height h, right? The nth ball will fall for a time of n minus 1 times ti. And if it's at 3/4 of h max, then it will have fallen a distance of a quarter of h. Oh, yes. Do you see why?
No.
So, okay, picture it this way. The ball that we're looking for is, if this is our total height, it's somewhere there at 3/4 of that height, right? Now we know that it takes 8t, however many units of time that is, for the first ball to hit the ground. We don't know which number the ball occupies, the one that's at 3/4 of the height. But if it's at 3/4 of h max, it has traveled a quarter of the height of that max. That's one. So in other words, for it to travel h max and it's at 3/4, it must have traveled a quarter of h max. This is now the nth ball. That being said, its motion can also be described using the same equation that we did there for vertical displacement. And if it's traveled a quarter of the h max, then we know that it would have traveled a half times 9.8 times n minus 1 times t, and that is squared. And that means the h would be, okay, that's not h max really, it's just h. That means the height it would have traveled would be 2 times 9.8 times n minus 1 t I, and that's squared. At this point we can't solve for n because it'll contain both h and t, which we don't know. But we can use the two equations we have to eliminate h. So we have h in the first instance and we have h again in the second instance, so we just equate the two. And that means a half times 9.8 times 8ti squared equals 2 times 9.8 times n minus 1 squared ti squared. I'm just following the learning guide here, but doing the math, we will have a situation where 8 squared equals 4 into n minus 1 squared. That becomes 8 is 2 into n minus 1. Then 4 equals n minus 1 and n equals 5. So in other words, the fifth ball is at 3/4 of the height of the tower when the first ball strikes the ground. Jeez, it really is a mental gymnastics type of question, eh? Yeah, but it'd probably be best to redo it again so that you think about it as you're doing it for self-study. Yeah. Right. I think we can proceed to do graphs of vertical projectile motion. So we can describe vertical projectile motion through a series of graphs, which are position, velocity, and acceleration versus time. So in other words, the y, the velocity, and acceleration versus time. But apparently in grade 10, we learned about the graphs to describe rectilinear motion with constant acceleration. And we used similar graphs in the last lesson with, 2 lessons ago with Mosiah. So because of that, we can apply similar concepts, and yeah, we're just gonna go over some revision from grade 10. And yeah, if we keep in mind that our velocity is displacement over time and acceleration is velocity over time, then depending on the graph, if we have displacement versus time, the slope is the velocity, and we don't have an area. Okay, so there's no area. If our graph is about velocity versus time, then our gradient is acceleration, and our area is displacement. And if we have acceleration over versus time rather, then we don't have a slope, but the area underneath is velocity. All right. And these graphs look more or less something like this. So if an object is not moving versus if it's uniform movement versus constant acceleration. Displacement versus time, velocity versus time, acceleration versus time. Time, acceleration, velocity, displacement. So an object that is moving, then the displacement is just that. And since it's not moving, there's no velocity. Let me make that orange. There's no velocity. And I'll make this one red. Then there's no acceleration. All right. I think I should just that. I think I should do for these two as well. So that's time, that's x bar, time, and that one is like that. All right. So displacement is green, This one is orange, and this one is red. Red for danger. So green. So if it's under uniform motion, that means a constant velocity, then the relationship between displacement and time is linear like that. Okay. I think mine is almost curved, so that's more or less it. And then if there's acceleration, then the graph becomes exponential. And for the velocity, constant motion, uniform velocity, that's constant. And if it accelerates, then that becomes linear like that. And lastly, for the acceleration, we don't have an acceleration still because we have a constant velocity here. But here, if our velocity is increasing, then we have a constant acceleration. Yabo. Okay, so these are a graphical representation of the equations of motion. If you have a graph, one for position, one for velocity, and another for acceleration, the corresponding equations should be able to be written down and vice versa. The types of graphs related to the equation of motion. Position is a parabola, velocity is a straight line, and acceleration is a constant. That's, I think, in the third row of graphs. Alright, so case 1, initial velocity upward. If we consider an object undergoing the following motion at a time t equals 0 seconds, so when the timing starts, that's its h. It has an initial position x equals 0. So here it's at a y equals y1. And then somehow it travels and reaches h max and then travels back down to the ground. Alright, so it will have an initial upward velocity of vi, and when it reaches the maximum height, that's v0, it falls down to a final position, which is y equals y final. Then the equation of motion for this would be change in y equals y initial plus velocity initial times the time plus a half times acceleration due to gravity times the time squared. It's important to notice that we are plotting position versus time, and the initial position xi is not necessarily 0. The position as a function of time will be given by the final displacement value, which equals the initial displacement value times the initial velocity times time, or rather plus the initial velocity times time, plus half the acceleration due to gravity multiplied by the time squared. As such, the initial position will shift the graph of the change in vertical displacement either up or down by a constant value. Okay, so in the event the initial position is not necessarily 0, then the graph can either move so that the axis shifts like that, or it shifts something like that. Yeah, that's what that means. The second graph is a linear function showing velocity as a function of time, where the final velocity is the initial velocity multiplied by the acceleration due to gravity, and this multiplies by time. So a graph looks something like that, where that is initial velocity and somewhere there is our final velocity. And that corresponds to a final time. That's the time somewhere halfway during the motion. That is 0. So if we choose upwards as positive, then the acceleration due to gravity will be negative. The slope, which is the coefficient of the time, of the velocity versus time graph is the acceleration, and the slope is negative, which is consistent with our expectation because our acceleration due to gravity is negative. So negative slope reflects negative 9.8 meters per second, or negative g if upwards is positive. Alright. And then the last plot we've got is acceleration. Definitely. So because our acceleration is somewhere there and it's constant, our graph will look something like that. So that would be Tm, and somewhere there would be T final, this is time in seconds, and over there is our acceleration. So because our acceleration is constant, we just have a straight horizontal line like that. Discussing these graphs takes a lot out of a person. Okay, so I'm gonna advise you to self-study these ones, and then if you have questions, you let me know. Then yeah. Okay, but I'm genuinely tired now. Yeah, so we can stop class here,
Okay.
and then Saturday